Hello, these are some notes I prepared for my students on chemical equilibrium. Okay, so let's go. So chemical equilibrium is something we're looking at following our initial discussion of kinetics. And chemical equilibrium is a dynamic process. The equil has a relationship to equal, but some things are equal and some things are not. So we have to be a little bit careful about our understanding of the word equilibrium. What is equal are the concentrations, the average concentrations of reactants and products over time. So, for example, if we have a process as shown here, where we have a reactant going to give product, we can see that it, or we can state, I guess we can't see it yet, we can state that at equilibrium, the molar concentration of reactants and products are equal in magnitude. Notice the symbol for equilibrium, these single-headed arrows. Oftentimes you'll see people butcher the notation, but we are not butchers, we're chemists. So the single-headed arrows are like this for equilibrium. If you ever see stuff like this, a reversible arrow, this just means reversible, but not equilibrium. Okay, so we're going to use the proper arrows for equilibrium. And remember from our discussion in kinetics, we know that when we're looking at elementary mechanistic steps and mechanisms in general, the equilibrium step is usually the fast step and therefore is typically not the rate determining step. At equilibrium, the rate of the forward and reverse steps are equal. So this is important. And as you might expect, there's a natural link between equilibrium and kinetics, and this is one of the major links, and we made this connection in the kinetics videos. Okay, so I'm going to scroll. Okay, maybe make this fit so we can see everything. Okay, so here's a visual. We can see two graphs. We've got on the y-axis, we have concentration. On the x-axis, we have time. And you can see for the equation, we have water in the gas state plus carbon monoxide in the gas state in equilibrium to give hydrogen gas and carbon dioxide gas. You can see that over time, as soon as you start the reaction at time 0, the molar concentration of reactants CO and H2O decrease, and then the molar concentrations of products CO2 and H2 increase. And during, where's my little stylus gone? During this part of the process, from here to here, let's see, from here to here, this is not at equilibrium. So this is not at equilibrium. Why? Because there's a change in the molar concentrations of chemicals. But you can see in the shaded part here, so after this dashed line, you can see that we have this fixed concentration. It looks like it's flatlined with time. It has a 0 slope. So here, this is at equilibrium. Because the change per unit time of the molar concentration is 0. Or the average, maybe we can put this to mean average. So you can change, you just can't change on average. Okay. And the diagram below just shows you a similar type of profile. So when you monitor the molar concentration of something, or remember from our definition of kinetics, that's the study of the change, the temporal change of a measurable observable. Once that measurable observable seems to be fixed on average over time, you have evidence that you've reached an equilibrium state. And you can see here in this diagram below, where it says equilibrium is achieved when the forward rate equals the reverse rate. So dynamically, reactants can become products and products can become reactants. Remember, the equilibrium arrow has this reversibility to it, but it doesn't have a net change on the concentration. Okay. Okay, so let's consider the following, and in good note fashion, there's a couple of typos in this page I noticed. So let's catch them together now. I'll try and catch them before I upload the notes to my students, but they didn't make it. I didn't manage to fix them in time for this video. Okay, consider the following reaction. 2 moles of iodine gas give 1 molecule of I2 gas. The forward reaction, we have a rate constant K1. Now, because these are elementary, we'll assume these are elementary, so we can assume that the molar coefficient is the reaction order. So this coefficient 2 should be a second order, not a molar coefficient 2 here. So that was a typo. So again, this second order in I is because of the molar coefficient 2 here, because it's an elementary step. We look at the reverse step. This looks good. We've got the molecule I2, which is first order because there's 1 molar coefficient. At equilibrium, we can set the rates equal. So again, this should not be a coefficient 2. It should be second order in I. Likewise, this should be second order in I. So that pesky molar coefficient just wouldn't let it lie with it. So hopefully we fixed them all here, and you probably would have spotted these mistakes anyway. And we can see a nice solid link here, the type of link that we made in our Michaelis-Menten kinetics video, that the ratio of rate constants is an equilibrium constant. So we have a ratio of rate constants is equal to an equilibrium constant. Equilibrium constants, you'll notice, are an uppercase K, and they actually have no units. Rate constants are lowercase k's, and they have units. So it's very easy to mix them together. So we're not going to do that. We're going to be very careful about which has units and which doesn't. But we can see a nice link between kinetics on the left and equilibrium on the right. One of many links that we'll make. Okay, so let me get my scrolling icon ready. Okay, so we've seen an equilibrium constant, so let's spend a few minutes looking at that. So equilibrium constants look at ratios. We've looked at ratios of concentrations. We could also look, and I guess there was another typo, huh? I just want to make sure I've caught all typos. This should be, I don't know if I caught that already, but just in case I didn't, that should be a second order in I, not a molar coefficient 2. We've already said that they are ratios. And so far we've been looking at concentrations, but we know that concentration is proportional to pressure. So we can also look at partial pressures, and we'll do that momentarily. So we'll definitely try and make that connection. Okay. So we can come up with general expressions. So in general, if you take an equation that says you have A moles of A, B moles of B in equilibrium to give C moles of C and D moles of D. In general, you can have the equilibrium constant K with respect to concentration. So that's what this lowercase c means, where it's the product of the products raised to their molar coefficients divided by the product of the reactants raised to their molar coefficients. So here we have c to the cth power, d to the dth power, divided by a to the 8th power, b to the bth power, where square parentheses means molar concentration. We could also have a similar expression using partial pressures, where we have Kp here, P means partial pressure. We have the partial pressure of the products raised to the molar coefficients divided by partial pressure of the reactants raised to their molar coefficients. And interestingly, Kc can equal Kp, but not always. So it depends, and we'll see how it depends in a second. You know, it obviously makes a lot more sense if you have a gaseous system to use Kp, but you can equally well, you know, so long as you can measure what you're putting in this equation, whether it be concentration or pressure, you can have either. They can be numerically equivalent, but they're not necessarily numerically equivalent, so we have to be on our guard. And we'll have a look at why one would be equivalent or otherwise in a second. Okay. So if you were given a Kc and you're asked for a Kp or vice versa, or if you want to understand why they would become equivalent, let's look at them. So let's recall the ideal equation of state, PV nRT, and let's solve for, let's introduce molarity into this expression. So we know that molarity, if we solve for N over V, moles per unit volume, we know that that's a definition of molarity. So we can say that molarity is equal to this. So let's put this in here. So molar concentration is moles per unit volume, which is pressure divided by the ideal gas constant times by temperature. So instead of our Kc, which remember was c to the cth power, d to the dth power, over a to the 8th power, b to the bth power, instead of writing that, we can do it in terms of P over RT. So we substitute this in for PC. So instead of concentration C, we have the pressure C, but we have this extra baggage of R and T. So pressure C to the cth power, pressure D to the dth power, pressure A to the 8th power, pressure B to the bth power. So that's straightforward. And then we want to factor out this commonality, this 1 over RT, which is common to all terms. So we can just isolate the partial pressure. So we factor out the partial pressure as shown here. Let me get my icon here. We factor out the partial pressure here. Sorry, we isolate the partial pressure by factoring out the 1 over RT. And again, because we factored out this 1 over RT, the 1 over RT also has this these coefficients C and D. Now, because we have a product of coefficients, we add them together. And then when we have the product of C and D, we add them together, but then we have the quotient of C and D divided by A and B. So when we divide coefficients, we subtract them. So if your coefficients are a numerator, we add them. So C and D as a coefficients as a numerator, we add them. Likewise, A and B as a denominator, we add them. But when we look respectively at the numerator and the denominator, we subtract them. Okay. Now I'm clicking all kinds of buttons erroneously. There we go, get rid of that. Okay, so now by definition of what we had earlier, if you recall, we said that K, the equilibrium constant based on partial pressures, was this guy over here. Well, that's what we have here. So we can call this thing here on the left Kp, and then we've got all of this stuff on the right. We can just rewrite it. So we've got Kc equals Kp, this factored out constant 1 over RT, and then this collection of coefficients, C plus D minus A plus B. And then we can essentially cross multiply to solve for Kp. So we take everything, this product here, this 1 over RT and all these coefficients here, and we can take them over to the other side of the equal sign. So the 1 over RT becomes RT over 1. And then we look at this coefficient bundle here, and what we have is just the change in moles. So we can call that delta N. So having this equation, and this would be the equation that you're actually going to use. So if you're the type of person that likes to memorize equations, this is the one that you will use. Okay. So Kp is is Kc RT delta N. Obviously, we know that Kp equals Kc if and only if delta N equals 0, because if delta N is 0, RT delta N just becomes 1. Okay, so we said earlier that Kp is not necessarily equal to Kc. It can be, but if and only if delta N is 0. So delta N is the change in moles of a gas. So if you have an equal number of moles of a gas as reactant and product, that's when delta N is 0. Okay, so let's look at an example. Okay, so you've got 2 moles of NO2 gas to give 1 mole of N2O4, and we are given some information. We are told from experimental data that the forward rate constant is a constant Kf, and then we can take the reactant NO2 to the second order because of the molar coefficient here and because it's elementary mechanism. The rate reverse is a different rate constant, Kr, N2O4 to the first order because there's a molar coefficient 1 here. At equilibrium, we set the rates equal. We can rearrange this expression. It makes sense to have the product N2O4 as a numerator, so that's why we take Kf as the numerator here, just because we want to favor the product concentration, because that's how we're going to state our equilibrium constant. So we can manipulate the rate expression here, and we can get our equilibrium constant. Which would be Kc. Now, if we wrote Kp here, so obviously this is a Kc. Now here, this would not equal Kp, right? Because delta N is not 0. So what is delta N? Well, delta N is going to be the moles of product, so it's 1 mole of product minus 2 moles of reactant, which is negative 1 mole, which is not 0 mole. So in this occasion, they're not equal. You could state the Kp, but you have to bear in mind it's not equal to the Kc. Okay. Values of equilibrium constant can indicate the extent that the reaction is reached. So for example, if we take this reaction, 2 lots of hydrogen gas plus 1 lot of oxygen gas give 2 moles of water gas. And we're told here that the equilibrium constant is essentially infinite, right? It's 3 by 10 to the 81. That's a ridiculously large number. It may as well be infinite. That means we would say that the equilibrium is shifted far right. So we would say equilibrium is shifted far right. And we would say it favors products. Anytime your equilibrium constant is greater than 1, essentially if your equilibrium constant is greater than 1, you would just say it favors products. This is a lot greater than 1, right? So the other example here, 2 lots of CO2 gas give 2 lots of carbon monoxide gas and oxygen. And here we're told that K is actually 10 to the negative 92. Well, in this case, I guess this comment, oh, let me get my stylus behaving itself. I guess this comment goes with that one. Just want to make that clear. Because 10 to the 81 is a lot greater than 1. This comment looks like it goes with that one. Okay, so for this expression, we're told that K is a lot less than 1. So we would say that equilibrium shifted far left. Favors reactants. And this is since K is less than 1. Okay. So essentially, this reaction wouldn't happen. So now it essentially means it wouldn't happen. It doesn't mean it won't happen, because 10 to the negative 92 is very small, but it's not 0. You know, if you had 10 to the negative $92, yes, you would be broke, but you wouldn't have 0 cash. So it's still it's still greater than 0, which is very, very small. Okay. Okay, so let's scroll ever downwards. And we can have intermediate K values, which again are in between. Let's look at manipulating equilibrium constants. So let's see the rules of the game, what we can do with them. Okay, so when a chemical equation is manipulated, its equilibrium constants also change. So take these 2 reactions here. We've got A at equilibrium with B, and we can write as written the the equilibrium constant, which is B over A. Both A and B are order 1, so we have an exponent 1 for both B and A. If we take the reverse reaction, where we just flip B and A round, we can write a different equilibrium constant indicated by the prime. And it would obviously be the inverse. So we don't take the negative, because as you look here, the equilibrium expression is a fraction. So when reverse a fraction, you take the inverse. So the relationship between the reverse reaction and its equilibrium constant and the initial reaction and its equilibrium constant are they're inversely related. Okay, so that's an important relationship. Okay. Let's see here. If two or more equations are added together, the equilibrium constant for the overall reaction is the product of the individual equations. So let's stop and look at this first bullet point. So let's say we have this equation. We have, let's call it equation 1. We have two lots of A in equilibrium with B. For equation 1, we have the equilibrium constant 1. So it's B over A squared. Again, there's a coefficient 1, not coefficient 1. Because there's a coefficient 1 for B, it's order 1 in B. Because there's a coefficient 2 for A, it's order 2 in A. If we then, we really don't need this add symbol here. It means add this equation, but let's look at it this way. Let's say we take equation 2, which is beta gives C. So the equilibrium constant 2, so many constants, so confusing. The equilibrium constant 2 is just C over B. If we were to add them together, then let's see. I want to make this clear. If we were to add them together, so if I were to essentially add 1 and 2 together, I'd add all the reactants and then I'd add all of the products, right? However, I've got an intermediate, so I could cancel B and B out here, so I'm just left with a net expression, which is 2 lots of A to give C. So overall, if I add equations, I take the product of rate of equilibrium constants. So if you add chemical equations, then you take the product of equilibrium constants. Okay, so we can see here that the overall equilibrium constant is the product of the two added equilibrium constants. So we've got the product here, and then you can see that B would cancel here, and we're just left with C over A squared, which is exactly what you would expect a priori anyway, because the molar coefficient becomes an exponent or an order. So take a second to look at that important relationship. While we scroll down. Okay, when the coefficients of a reaction are multiplied, the equilibrium constant is raised to a power. And this is just from the order. You can see basically the origin of this. Multiplied, this essentially is a coefficient. And then raised to the power, this is essentially an order. And you can see this from the kinetics videos. So we saw in kinetics videos. Okay. So again, we've got 1 molar coefficients here. We have orders 1. We have two molar coefficients in the second reaction, we have order 2. And we have half molar coefficients here, we have order half. Okay, so that's straightforward. Not the first time we've seen that. Okay, law of mass action and mass action expressions. The principle relating chemical equations of a reversible reaction to its mass expression is the law of mass action. We can have in general mass action expressions that we label Q or K. Q essentially stands for quotient. Again, let me select. So Q stands for quotient, which means fraction. And we saw that the equilibrium constant is a fraction. So Q is not a constant. K is a constant. And we can start to refine some of the diagrams we saw earlier in this video when we look at the difference between Q and K. Okay, let me try and make this a little bit smaller. Maybe that's still big enough. Okay, so let's look at Q and K. So let's take this chemical equation here. Water is giving CO. Actually, I don't need to make it that small, do I? Water is reacting with carbon monoxide to give hydrogen and CO2 gas. Let's now go to this reaction profile. If I start with just water and CO, so from the reactants, then I would expect the concentration of water and CO to decrease with time. And I'd expect the concentration of products to increase with time, right? So reactants start at 100% of their value and they decrease with time. Products start at 0% of their value and increase with time. But this is not a constant case. I'm not at equilibrium here. So I would expect this part of the process to be Q. So here I could write a mass expression, but it wouldn't be an equilibrium mass expression. I could write a mass action expression for A here, but it wouldn't be constant, so it would be a Q value. The actual equilibrium is in the middle. This is where the molar concentrations are constant. So this is when Q is equal to K. So when Q is equal to K, I'm at equilibrium. When Q is less than K, my equilibrium is going to shift right. And vice versa, if I come from a state where I have, I've added too much product, then I could reverse on this process here, and I could actually shift back towards equilibrium by shifting left. So I realize I've said a lot of stuff here. I don't need to annotate everything I've just said because it kind of prefaces what's going to come next, Le Chatelier's principle. But let's make a couple of statements here. So if Q equals K, I'm at equilibrium. So that would be no shift. If Q is less than K, you would shift left. Sorry, if Q is less than K, you would shift right until equilibrium is reached. Then no shift. So as soon as you reach equilibrium, the shift stops. steps, then no further shift. And then finally, if Q is greater than K, you would shift left. Then no further shift. Okay. So Q covets K. Q wants to be K. Q is essentially what happens when equilibrium is trying to establish itself. So you could write down the same expression. So for example, for this chemical reaction, if I remind myself what the chemical reaction was, let me see what the actual chemical reaction was. Yeah, so you could write down everything's a gas. I may as well put it as a gas then, hadn't I? I was going to do concentration, but I can keep everything as a gas. Okay, so the reaction was the partial pressure of hydrogen gas multiplied by the partial pressure of CO2 gas divided by the partial pressure of water gas almost wrote that correctly. Partial pressure of water gas and the partial pressure of CO gas. Okay. You could write that, but that is not a constant. It's not a constant value because it's Q. And I guess it's QP, not QC. If we wrote KP, this would be the partial pressure of H2, the partial pressure of CO2, the partial pressure of H2O, the partial pressure of CO. So whereas Q is not a constant, K is a constant. Now, in this case, Kp is equal to Kc because delta N is 0. Because we have 2 moles of product, 2 moles of reactant, so 2 minus 2 is 0. So we would know that numerically the two expressions for law of mass action would give the same value. Okay, so let's continue our discussion. Le Chatelier's principle. So there's not too much more left now in this video. And I'll do a separate video looking at some calculations, a little bit more. Let's look at Le Chatelier's principle. Okay. Le Chatelier's principle states that if a stress is applied to a system at equilibrium, a reaction will occur and there'll be a shift in equilibrium to oppose the stress. And a stress is anything that changes concentration. So the common stresses that we'll see are a temperature change, a pressure change, a volume change, and that's pretty much it. Okay, so let's have a look at some examples. Concentration stress. So possible changes. So let's say you have a system at equilibrium A to give B. If we were to increase the concentration of A by adding more A, then suddenly Q would be less than K, so it would shift right. If we were to add a greater concentration of B, we just dump more product in, then we would make Q greater than K so that the reaction would shift left. And if we removed A, it would be the same as adding B. So we'd have a common shift to the left for the third bullet point here. And then finally, if we remove B, it's the same as adding A. And just so it's clear about this Q and K, I would definitely encourage you to have the idea of a Q in mind. So if we actually just remind ourselves what Q looks like, it would be B over A, right? So if I add more A, then the concentration of A increases. So we increase denominator. If we increase the denominator, it means that the actual quotient Q decreases. Okay. And we know that initially QC equals KC because it's at equilibrium. Okay. So initially QC is equal to KC because we're told it's at equilibrium. So when we say adding more A causes Q to become less than K, it's because of this. Q now is decreased below the K value, etc. So this is the type of argument that you would scribble on a piece of paper to understand these bullet points. Okay, so let's consider this example. So we've got water gas and CO gas to give hydrogen gas and CO2 gas. And let's say the stress imposed now is removing CO2 gas. Well, if we look at the expression, now we could actually, it would probably serve us best. It doesn't matter here if you call it K or Q, but let's say that this is Q. We could even call it Q. Then if we've removed CO2, then the concentration of CO2 has gone down. So basically, if we've removed numerator, then that implies that Q has decreased as well, right? So that's why we say that Q is now less than K, and so it has to be restored. So to oppose the stress, you have to make more CO2. So to make more CO2, what would you do? You've got to increase the forward rate. So this dynamic process of shifting right, we shift right by temporarily increasing rate forwards. So remember, at equilibrium, the rate forwards and rate reverse are equal, but when you're shifting, they're not equal. So when you shift, it implies that rate forward is not equal to rate reverse, right? So the rate forward causes you to shift right. The rate reverse causes you to shift left. If you're at equilibrium, your rates are equal, so you shift nowheres. So if you want to shift right, or if Le Chatelier's principle is telling you you're shifting right, then your rate forward is greater than your rate reverse. And if you're shifting left, your rate reverse is greater than your rate forward. Okay. Pressure stresses, changing volumes will change the partial pressures, etc. If you decrease the volume, you essentially increase the pressure. Now, one way to consider this is here you've got 2 moles of gas. Here you've only got 1 mole. So this 2 mole is the high pressure side, and this 1 mole is the low pressure side. So if you were to raise the pressure, which we're doing here, we're decreasing the volume, which effectively raises the pressure, then you're going to stress the high pressure side, because like stresses like. And what I mean by like stresses like, for example, on a cold day like in the wintry abyss that I'm in right now, on a cold day, the cold will stress you. On a hot day, heat will stress you. If you're under pressure, more pressure will stress you. So more pressure will stress the high pressure side, so we'll have a shift towards the right, as shown here. So you can pause the video and think what I've just said a bit more than I have time to dwell in this video. Okay. So you can look at pressure yourself. Temperature. Temperature stresses are unique. These are the only types of stress. So essentially, what would be the best way to say this? Kc and Kp are constants at given temperatures. So you can have a brand new constant every time you change the temperature. And it's unique as a stress. So if you alter the pressure, you will have a dynamic change from K to Q, but you'll always go back to the original K. You change the temperature, you'll adopt a brand new K because it's temperature dependent. And this is one of the reasons why, it's not the only reason, but it's one of the important reasons why temperature in biology is so important. You know, biological chemistry or life in general has a small tolerance for temperature changes, because every time you change the temperature, you establish a brand new equilibrium constant. And if you think back to your Michaelis-Menten kinetics videos, that would be a brand new Michaelis-Menten constant, which is going to affect the rates of all that biological chemistry. Not all of which will be commensurate with life. So one of the reasons why biology has such a limited window of temperature values. Okay. Here we have the Haber-Bosch process, the synthesis of ammonia. Nitrogen and hydrogen gives ammonia. We're given an enthalpy for this process. We notice that it's exothermic. So because the temperature is negative, we know it's an exothermic process. So we know that heat exits from our first semester general chemistry notes. We know that when heat exits a system, it's exothermic. We can write heat, therefore, as a product. So heat now is a product. So importantly, we know that we have a hot side, and therefore we have a cold side. So in the previous example, we had a high pressure and a low pressure side. When we consider temperature as a stress, once you know it's exothermic, the products are the hot side and the reactants are the cold side. Conversely, if it were an endothermic process, the products would be the cold side and the reactants would be the hot side. So we can now understand these effects on temperature based on that allocation of labels. If you have an exothermic, so let's look at exothermic first, because I've just mentioned exothermic. If you have an exothermic reaction, then the products are hot. So increase in the temperature will stress the product side out, so you'll shift left away from the products, because at that point Q is greater than K, so you will shift left. You will then reestablish a brand new equilibrium constant. Conversely, if you have an endothermic process, then the products are heat is a reactant, so the products are cold. If you increase the temperature of an endothermic process, the products are cold, so you will stress the left side, so you'll shift right again, because you'll move away from the stress. So take a second to think about what I said then, and look at what's in this diagram here. And in the next video I post, there'll be some example calculations, no doubt. Here's a nice summary of the stresses that we've talked about. And as you look at these stresses, just bear in mind that you always move away from the stress. Okay. So I think we're moving towards the last couple of things. Yeah, this is the last couple of pages in this video. The effect of a catalyst on equilibrium. So we said in the previous kinetics videos that catalysts can alter the rate of a chemical process by altering the activation energy here. So here we can see an energy diagram where reactants in the uncatalyzed process follow this blue line to give products. With the catalyst, we can redistribute that energy. We don't destroy energy. You can't because of conservation of energy. But we can redistribute it and have smaller activation energies, as shown with the red line. Notably, we don't affect the energy of the reactant or the product. We just affect the energies of the intermediates or the transition states as shown here. There are no intermediates shown here, but the transition states shown here. Notably, because a catalyst doesn't affect the concentration, well, actually, it doesn't show you here. Catalysts don't affect the equilibrium constant, they affect the rate of attainment of equilibrium. Let me write something. I thought it was going to say something, but it doesn't. So catalysts don't alter Kc or Kp. Catalysts do alter the rate of Qc going to Kp. Qc going to Kc and or Qp going to Kp. So it's the rate of attainment. That's what a catalyst does. So for example, seeing as it doesn't show you here, let me show you. I'm going to actually scroll back to a graph that I can actually use to demonstrate this. Yes. So if we go back to this graph real quick, let's say this is without a catalyst and we've got equilibrium here. If I added a catalyst to this graph here, it would just do everything a lot quicker. So pardon my shaky hand there, but this is supposed to be smooth. Okay. So if the equilibrium was established here, this would be with a catalyst. Notice I don't change, if I looked at the equilibrium expression, it would still be, H2, if I look at Kc here. It would still be like this. But I would get there quicker. So I would have a shorter Q stage and a longer K stage with the catalyst than without the catalyst. So hopefully that was straightforward. Or hopefully that was clear and straightforward. Okay, so to get back to where we were, there is one other thing I don't recall ever saying, but it's probably, maybe it was here and I just didn't notice it, but something I would definitely point out in these equilibrium constant expressions. Yeah, I don't think it ever was said. That's not too great. So a note, we only consider aqueous species and gases in K expressions. So we can essentially just ignore solids and liquids. So only ever worry obviously in either of this type of equilibrium expression, you only need to consider aqueous species or gases. It just so happens that's all we saw here. But if ever you have a liquid or a solid, just ignore it. You don't even have to entertain why. It's really not worth even looking at why. You can quickly think why, but I would just say ignore it. Save yourself the hassle. Okay, so moving on to that final page. Now I've got that off my chest. The final page in this initial equilibrium video is this here. So calculations based on K. If ever you need to do a calculation, always assume, or it's always good advice, to assume that you have Q. And then if you measure the Q at different points during the process and it never changes the outcome, the numerical outcome, then you can augment your understanding of Q to say, okay, well, that Q is actually a K. But it's always good to assume that you have a Q to begin with. And then eventually we're going to do some calculations where we would construct ICE tables, where ICE is an acronym for Initial Change Equilibrium. The next video, we'll look at some examples where we use ICE tables. And then just a heads up, you are going to have to remind yourself about the quadratic equation. This is something that you'd have to know and be able to use. And again, I will give you some examples of using ICE tables and using the quadratic equation in subsequent equilibrium videos. Will we always have to use the quadratic equation in equilibrium videos? Nope. There's essentially going to be a hierarchy of what I would suggest that you try. I would recommend using the quadratic not as a last resort, but as one of your latter resources. Sometimes you can get away with using an approximation, but more on this approximation in subsequent videos. It's this last bullet point here. But when a shift is small with respect to the equilibrium constant itself, we can get away with ignoring the shift and verifying that it's less than, essentially we use a statistical idea where we can say, we can assume an alpha value of 0.05, which would correspond to this 5% shown in this last bullet point here. But much more about that in subsequent videos. Let's keep this one as short as we can. Okay, so that will be the end of this video.